So these are the two coordinates of the boxes. So I will try to print that along with the IX and IX0 and IX1. So let's see if I am calculating this correctly. Before we move on, it's good to check that this is being calculated correctly. Step 10. Okay, so if you look at the numbers, so when it's 0 and 1, it's like here, and when it has a big number, 6, so it's still within, yeah, I think these numbers look correct. At 1, it should be, so when it's 0, it's like halfway, and you're also dividing that by 1/8. So the size of the box is 1/8, but the point is at half of that. So that's why there's this 0.5. So by adding this here, I think I'm getting the center coordinate. You see, because the center is like, it's like half in the center of the box. So if the length of the box is 1 over nx, then sort of adding 1.5 before dividing will give you the center of the box, if this number goes from 0 to 7. Okay, so now we have the center of the box. And now actually I don't need to store this in like a separate value, because I'm immediately going to subtract here x, wait. So I'm going to put this inside the loop for x, for the bodies, and then I'm already going to subtract immediately from because what I want to know is the distance between the center and the box. So and the particle. So once I calculate this thing, I'm immediately going to subtract from xj and yj. J is the index of the particle. Okay, so I'm getting the dx and dy, sort of in the same way that I'm getting it for the other kernel. So dx and dy. And from dx and dy, actually, I can calculate r, so I don't need to pass r. I just need to pass here dx and dy. Or maybe I should pass it before q. Or no, I'll just pass it after q, because it's easier to change for the other kernels too. So, okay, so I'm going to do this for all the other kernels too, except M2l is already calculating this, so I'm just going to pass that. But I'm going to calculate dx and dy for the other boxes, and then keep passing them into the new kernel that I wrote for each case. So let's go to the P to M kernel, although it won't be used yet, because we're still doing only the first term. But I'm going to just write here double dy, and I know I'm going to do that for the same thing. So I'm just going to go ahead while I'm up here and just change everything so that it has dx dy, and then here, instead of inputting r, I'm going to input double dx and double dy, and then from this input, I'm going to, inside the function, calculate r. I should be doing this for all the other kernels too, but dy. Okay, so r can be calculated from dx and dy like this. So I'm just going to keep adding double dx and double dy to all the kernels that I've defined. Although they won't be used for most of the kernels. And again, for P2P, I can again calculate r from dx and dy like this. Okay, now I changed everything in the definition, function definition, but I haven't changed all of them in the function call here. So now I need to make sure I'm calling dx and dy. So now I need to do the same thing for M2m. But maybe there's a better way to do it for these parent-child distances, because no, I'll just do it in a simple way. Yeah, I already have nx, and I need to calculate the get ix for level L. For cell I, like this. And then the parent cell is what? Ix. So Ix divided by 2 is the number of the parent cell, but it should be divided by a separate nx, right? Okay, so this plus 0.5 divided by nx is the, so this is the position of the current cell, and for the parent cell, it's Ix divided by 2 plus 0.5 divided by, not by nx, but nx divided by 2, because it's like parent has half the number of subdivisions. Okay, I think I can simplify this equation somehow, right? Because if I know this, and if I know that I'm dividing here by half the nx, is that equal to multiplying this by 2? And this by 2, which becomes plus 1. Well, okay, I won't change this until I have this working. Once I have everything working, it's easy to confirm by just running the code. So now I'm just going to do what I'm sure will work. Okay, so the function is the following. So for the parent, you need to do plus 0.5 still, but you divide by half the nx, like this. And nx is always a even number, so dividing by 2 is always okay. It will give you the correct number of subdivisions at the parent level. So the logic here is I am subtracting the current level from the parent, the current coordinate. I think I need to subtract the other way. I need the destination to be first. So let me change this part. The parent coordinate needs to be first. It needs to be the part where you subtract from. So here, I'm just changing the order of the subtraction. I'm moving the parent forward. So this part needs to be in the front. The parent needs to be in the front. I'm subtracting the child coordinate from the parent because the destination needs to be in the front. Okay, so now dx and dy I have. Okay, so I'm just inputting the dx and dy that I calculated here into the function like this. Okay, maybe I can even put this whole thing inside this if statement because it will save time to calculate. Although it's not a very critical part of the FMM code. This part will take almost no time anyway, but okay, so dx and dy I've calculated for P2M and M2m so far. The good thing is L2L and L2P are symmetrical from P2M and M2m, so I can just copy and paste these things for P2M and L2P. So here, but again, the direction of the subtraction needs to change because for the L2P, I need to be subtracting from xj and yj. Because that's the definition of, and then input that to dx and dy like this. Okay, so this is for L2P. I just copied from P to M. Again, also from M to M, I can just reverse the direction. So this part that I was subtracting, I will now put in the front and subtract from. And this part here, I put in the front and subtract from. So here now, this is the dx and dy that needs to be done for the L2L. I'm subtracting the parent coordinate from the child's coordinate. And for M2L, I already am calculating dx and dy. So for M2L, I'm just going to change this r to dx and dy. And I don't need to calculate r here anymore. Okay, and then P2P, I am also calculating dx and dy here, and I don't need to calculate r anymore. So also same here, dx and dy for the check answer I am calculating already, so I don't calculate here. Okay, so now everything should be working. Step 10. I think I typed something wrong somewhere. 193. I forgot to put the L2L. I forgot to put these braces. Okay. Step 10.c. Still giving the correct answer. So I have successfully added these distance vectors, dx and dy, to all the functions. So we're almost there now. Now the final thing is to just change the kernels that use these things to calculate the high order expansions. And I've prepared them already. Well, I've written FMM code somewhere else, so I'll just take it from there. But the basic structure you follow, right? The only thing that I'm going to change now, going to step 11, is to just change what's inside L2L or L2P or all these functions to something different. Everything else will remain the same. Except I think there's one more step, like an intermediate step that I can take, is L right now is just one number per cell, right? It's just, I'm indexing it by just the cell index, and I'm assuming inside all the functions, if you look at my kernels right now, I am saying, so for all of these ones, I'm treating these m's and l's as scalar values. Okay, there's only one number. But I want these to be like an array of all the expansion coefficients. So, for example, if I'm doing like p equals 6, this needs to be like an array of 6, for example. Okay, and also, there's another small detail about the kernels that I'm going to introduce. They're going to be complex numbers. Okay, so maybe I should explain this to you before I introduce the kernels, because the kernels I wrote here were not complex numbers. But so when you do this kind of Taylor expansion in 2D, like 2D Taylor expansion, it turns into many terms if you're using a real number for these values. But consider if this x was a complex number z, which is equal to x plus iy, which is like, so if you use a complex number, you can express the two coordinates with just one scalar complex value. And then this Taylor expansion turns into actually a 1D Taylor expansion, and everything becomes very simple. So although complex arithmetic is introduced, it actually simplifies these vector powers and vector factorials and vector summation indices to a scalar. So I'm going to introduce a complex number expansion. Well, it's the same thing. I'm just going to introduce these equations, except for x, I'm going to use z, a complex number that's a scalar, and not this vector x, which is xy. It's not a set of two numbers anymore. So the math becomes simpler, and also the reason is because I already have a code that calculates that complex one. So before I go to this step of introducing the complex numbers and the proper high-order kernels, I'm going to introduce one last intermediate step. So step 11 will introduce, let me introduce, so first I will copy step 10. I'm done with step 10, so let me upload step 10 like I uploaded step 9, so that you can start from there if you didn't follow. So step 10, yes. We'll go to my Google Drive, and it's updating. Okay, now step 10.c is uploaded, so everyone can download and just run. Now I'm going to move to step 11. Okay, so I will now, step 11 is complex coefficients. Okay. So what do I change? I change m and l, these two things. So it says double here, but I'm going to turn these into complex numbers. And to use complex numbers, wait, I have a complex number in C++. So complex numbers in C is different, right? I need to use, is it the same? Double complex. Okay. Include, I'm going to include the header file complex.h because I'm going to use complex numbers. Okay. And then all of these doubles will turn into like a double complex numbers. Oh wait, I'm not entirely sure how this, because I don't usually use C, so works like this, right? Double complex, and that becomes a type. So yeah, let me change M to double complex, just a test and see if it breaks anything. Okay. Okay, so I have to change only a few things, I think. I'm not sure if I can do like double complex, assign 0 to these numbers, but we'll see soon enough. I just get warnings. I'm getting the correct answer still, but okay, so I think this is still okay as a code. So I'm going to now change all the, both the M and L to double complex because it seems to be working. Okay, now let's see if step 11.c is still, oh good, the warnings went away. Okay, now it's still giving the correct answer. So now I've changed M and L, those two arrays that were doubles, they are now complex numbers. Okay, so how do I printf a complex number? I just want to make sure I can. Oh, so you need to separate the real and imaginary part? Yeah. Okay. So now the next thing I want to introduce is to make these arrays, change the size. They were scalars, but now I want to make them like size p times the number of boxes. So I'm going to change all of the M and L so that they get indexed by p. I'm going to define p here. So p, let's use 3 or something. Okay. P is the order of expansion. We will introduce the order of expansion p now. And so I'm not changing anything inside the equations yet. I'm just changing the data structure to complex and then to an array with p numbers in them. Okay, so M and L are now two-dimensional arrays of p by number of cells in the whole tree. Okay, and when I do this, I am passing, by doing this, I should be when I index like this, I don't need the AND, right? So this will be a pointer to the first. Yeah, I think I just need to get rid of all these AND. So all the parts that I had AND for the, or not the U, because I'm not changing the data structure. Okay, so the interface is now changed. I am passing a pointer to the first element. So this thing here that says M star is now I'm actually passing in like the first index of the array. So there should be, this should be like, if I change M0, because essentially M0 is the first term, and this is what we are calculating here. So all of these equations we're just calculating, and I need to make all the M's and L's stars now, even the ones that I'm just reading. They are all arrays, so I'm passing the pointer, and I'm inside. I'm just referencing the first zero, or the zero element number 0. Like in all these things, I change them to star, and then I index by 0. Change the input to star, like also this one to star, to a pointer, and then I'm going to index all of them with 0. I think this should be okay. So I've changed all the interfaces to make it, I'm initializing. I didn't update the initialization part. That's why it's complaining. So it's saying you're treating them as, yeah, so why don't I just initialize them like I should with like a 2D thing. So I need to initialize the whole, initialize the whole 2D array up from 0 to like p minus 1. So because it's size p times, the number of cells. So okay, now I've changed that, so it shouldn't complain. Oh, okay, I seem to be doing something bad. Okay. I think I made some yeah, these should all be pointers, right? So why is it not working? So the compiler is not complaining, so there's nothing syntactically wrong. Maybe this needs to be P? I'm not sure. Let me print if and see if it's stopping here. Because I just changed it to an array. That's the only thing I changed here. Okay, so yeah, it's likely that it's failing here, I think. So let me check if this is true. So it's saying there is no M0, I think. Yeah, so it printed the before but not the after, so it's giving the segmentation fault here. So oh, maybe I have it in the wrong order. So maybe P should be like because the name should be oh, but either way, I'm only accessing the number 0 element, so it shouldn't complain. But let's see if this is... Ah, okay, yeah, I think that was the... So now it's working. What I did was I just flipped the order of the two-dimensional array for M and L to have, like, the first index is the cell index, and then it's like a, yeah, so it's an array of like MP arrays. So I'm indexing the, yeah, MP array, the index of the MP array. Okay, and the P is the ladder, yeah, so that, like this. Ladder index. Okay, so now I think we are ready to just plug in the kernels I have. So I'm going to save step 11, the working thing, as step 11, and then the final step 12, I'll just swap the inside of the P2M, M2l, M2l, M2M, M2l, and L2L, L2P, P2P, all the kernels, so that it will work. So step, and I'm going to upload step 11 now to the Google Drive. Yeah. Okay. I think unless something goes terribly wrong, I think we have enough time to finish the full FMM because it's just changing the kernels. Okay. Step 11 is uploaded. Okay, final step, number 12. High order kernels. Okay. So now I have these kernels P2M and so on. So I have 2D kernels inside another code. Okay, P2M. Except it's written in C++ with structures, so I need to somehow extract just the calculation part here. dx2 is the dx and dy vector that I'm passing, so I need to first turn this into a complex number. Yeah, right. So double complex z is dx dy. Can I do this? Let me first check if this is okay to do. No, this is not okay to do. Okay. Yeah, because this is C++ type of initialization. Needs to be like big I is like a predefined variable or something. Like this. Maybe this is how. Okay. So then, now that I know how to use this, I'm just going to copy over all the contents from this. I'm defining also another thing that is for calculating the powers. So this thing, double complex pow z is like the power. It starts from 1 and then it's for calculating the power, because there's a power in the Taylor expansion, so I just using this to accumulate the powers. Okay. And now I just need to loop from Okay, so I'll loop from n to from n1. So 0, 0 I'm already calculating, but the high order terms I need to calculate in loop. Like this. And p is only defined outside, and I'm not passing p, so this, I need to make sure to define p as a global variable or something. Okay, so this is a new P2M kernel. And changing just this part won't harm the other parts of the code, because it just, all the other parts of the code only reference M0, so it doesn't matter what I put inside the high order terms for M. It's just not going to use them. So the answer should still be the same. I'll check if this code is working. Yeah. So I'm just going to define P like outside, like here, because okay. Okay, so still I'm getting the correct results. And now I have a proper high order P2M kernel. Well, we don't know if it's giving the correct answer yet because we haven't confirmed, but I think it's okay. Now let's move on to M2l kernel. There's one thing that's different. It's subtracting the other way in this kernel. So I should make sure. So it's in my other kernel, for some reason it's subtracting this other way. So I should match the definition here, because okay, so P2M, the dx and dy were defined like, well, you can pass minus dx and minus dy. Maybe that was faster, but okay, so now everything is matching. The definition is matching, and I am going to move to the M2m kernel, which is this part here. Okay, so same thing. I'm defining the z again, and let me make sure that the direction again is the same. So cj. Again, I think the direction of the sign of dx dy is opposite for my calculations here. So I'm going to just pass in minus dx and minus dy. Okay, so M2m is, I'm going to use the same definitions of these z and power of z. And here we just need to loop over, what is this KML thing? It should be okay to just use n I don't understand why I'm using this strange number, or a strange variable name. Okay, so again, power of z is z divided by n, and mk plus equals mk minus n times power of z. I think that's what it says here. Yeah. Okay, so that it's very simple change. It's not a very complicated code. I just added, the factorial. Actually, the pow z is like calculating the power of z, and also divided by the factorial of n, because n is increasing from 1 to k, and then it's being multiplied to the original number again and again. So it's taking the power of z and factorial of n at the same time and putting it in power of z, which was the definition, if you remember. 1 over factorial n times the power of the vector x, xj prime j double prime. So now we have all these values. Let me just make sure that n could be start from 1, so this will always be smaller than p minus 1, right? pk could be no, where is the loop for k? I'm missing the loop for k. Yeah, there's another loop outside here for k. I'm sort of missing an outer loop for k. Yeah. Unless I calculate this outer loop for k, I'm only calculating the first term of the parent expansion. So I need to change this thing here, from 0 to k. Okay, so now when k is 0, it just calculates the original thing. And yeah, so this should be okay. So now it's calculating mj. Okay, since I'm using the variables mi and mj, I need to, so this is mik plus equals mjk, and then looping n from 1 to k, calculating the factorial and the power of z, and then multiplying that to mj, k minus n. Okay, good. So now I will check if this is working. Oh, and we could take a short break, like a 10-minute break, if this compiles, because we have another 50 minutes to do M2l, L2l, and L2p, and P2p. Okay, good. It's working. So let's take a short break. But I think we have enough time to finish everything. So I've just added the P2m, M2m kernel. If you remember, if you think of this z as like the scalar, vector, distance vector, and remember the original definition that we covered in the first lecture. Just so that everything makes sense to you, even though I introduced the complex numbers. So basically, it's still doing the same thing. So we have n factorial So this is the P to M kernel shown here. N factorial times the x to the nth power. This is being calculated here because I'm taking the power of z, which is like, you can think of it as the x vector, and if I multiply equal n times, it's going to turn into the power of z to the n. And this part, n is increasing from 1, 2, and 3, and then it's being divided by those numbers with the multiply equal. So it's like the factorial of n on the denominator side. So once you multiply that to q, you see that it's calculating exactly this. And it's just looping over all the points inside the box. So every time it does a plus equal, it's just adding to this, like this summation mark here is being done on the outside loop. So inside loop, it's just generating all the terms for n. And it's storing each n for different n into a different part of the array, so mn. And so if you look at the m2m, you see that it's calculating exactly this equation here as well, although the difference is that x vector here is expressed as a complex number z, but that doesn't change the form of the equation. So n minus k factorial is being calculated this should be n minus k. Instead of the n, because it looks like I'm calculating the n factorial there. Or maybe I swapped variables. Yeah, okay. I think I swapped, so I changed the definition. So the reason why n is going only up to k is, well, it's still strange because m to the k. So this one is turning into k minus n, and this one is turned into n. The k is okay, but it's like a redefinition. So if I change k to n, it would look like this. And if I change n minus k to k, it still looks a bit different from this one. So n goes from basically 0 to k. 0 to k goes from 0 to n. I wonder what happened. But okay, so once I figure out what happened with the n minus k power here, you can still see that it's calculating the same kind of factorial here and the power here. So this pow z represents this part here, and mk is written as k minus n because I think the definition is slightly different for the k and n. But anyway, this will calculate all the necessary terms for this equation. So all of them will be in this new array mi now. And so I'm calculating this thing. Okay, so the next task is to calculate this one, and this one. So because I'm just copying from a code that's working, I'm sure the end code will work. And now that we've successfully added all the complex stuff and it's running with the complex, it's just a matter of adding 1, 2, 3, 4 more equations in the next 50 minutes. Okay, let's take a break for 10 minutes and we will resume. Well, you can, try to download. I'll upload this code as it is now, and you can try to check if it's working. Okay. Step 12 is uploaded.